Okay, I'm recording now. Oh my God, I keep forgetting. All right, let's do this again. Okay, there we go. So first, the second example right here, we want to prove that A intersect B union A intersect complement of B equals to A. So we want to do it with the set laws, okay? So let's look at my table and see if we have anything here that might be helpful. Okay, so anybody see any laws in here that would be helpful in simplifying this expression right here? So we want to take the left-hand side and simplify it somehow.
The opposite of the distributive, maybe?
Yeah, the distributive law is good, right? So if I look at the distributive law right here, I see that this part right here is what's given, and I can go opposite to basically to factor, right? So basically I'm going to factor the A, okay? So let me go here and see how that would happen. Right, so yes, exactly, we have A intersect B united with A intersect BC, like the A set appears in both of them. So basically this is A intersect B U B C. Okay, and then think if you distribute, then the intersection is going to distribute with the union in the middle. All right, I think this is a law, right? So this B united with BC is the universal set. So I end up with A intersect with the universal set. And this is also a law that says if I take the intersection of a set with the universal set, then that's the set itself. Okay, so here, let's see which laws we used. All right. Okay, so the complement law. So say if I do the union of a set with its complement, that's the union. So we use the complement law there. And also the identity law. So if the intersection of A with the union is going to be the set. Okay. All right, so that's the proof for this one. All right, so I don't know. I like this way of proving sets better than any others. Like Venn are fun, but it takes a while to draw, and they're not that great if you're more than 3 sets. And the membership tables, they're kind of cool too, but you have to draw all those ones and zeros. And the one with the definitions where you have to prove that it's a subset and then the other one is a subset, they're like a bit too long. So this one using the laws of set theory are probably the most useful ones, I think. Okay, any questions with this one? All right, let's go to the next example. Okay, so prove that if A is a subset of B and A intersects C is not the null set, then B intersects C is not the null set. Right? So this one, I don't know how I would approach it with the set laws above. So this one I would do like a proof by definition or even a Venn diagram. Okay, because it's sort of, I think the laws above are useful if you're trying to prove equality, but if you're kind of trying to prove like other relationships, then they're a bit more awkward. Okay. So let's look at doing this by definition. Okay, so by definition, you're basically looking at an arbitrary element, okay, of sets. Okay, so we're going to take this premise right here. Okay, so if A intersects C is not the null set, then that means that there is an element in the intersection of A and C, okay, because it's not empty. Okay, so this is X is part of A and C. Okay, so there exists an X in that intersection. All right. Now, if there's an X in that intersection, that means that X is going to be in A, and that X is also going to be in C. All right. So far so good. Okay. So now we know that A is a subset of B. Okay. So because A is a subset of B, this means that if X is in A, X is also going to be in B. All right. And then I also still know that X is going to be in C. Right. So now because X is in B and X is in C, that means that X is going to be in the intersection of B and C, which means the intersection of B and C is not the empty set because it has this element X in it. Right? So here's the proof for that. Okay, so kind of just using this kind of by definitions where you take a member of a set and you basically show that it has to be in these other sets to lead you to the conclusion that you want. All right, any questions with this one? Good. Okay. Yeah, go
what
ahead.
strategy to approach? Like, if I was looking at that, I'd be completely, I wouldn't know where to start or what looking for.
Yeah, so it's like I said, because I'm now like proving an equality, then sort of the laws in the table are not that useful. So I would, like a Venn diagram would be good to start with because you can picture things. Okay, so maybe let's look at a Venn diagram here. So Venns are always a good starting point because it helps visualize. Okay, so let's say I have these sets. A is a subset of B, and A intersects C is not 0. So let's call this B, and I'm going to call this C. And it says A is a subset of B, so it's inside B, but it's the intersection is not empty. Okay, so that's the intersection of A and C. Okay, so can I prove that the intersection of B and C is not empty? Okay, so I mean, the way I drew it, the intersection of it was not empty, but you can see that visually, you can see that because A is inside B, this circle for B has to intersect part of C also, right? So kind of just drawing the Venn diagram sort of gives you a visual of what's going on. Maybe like this is not enough to kind of give a formal proof unless you write a bunch of stuff. But that basically would lead me into this. It's like, oh, let me take a element of X that's in the intersection here and prove that it's also in the intersection of B and C. So like with everything in math, I think the more exposed you are to different problems and their solution, the more you learn strategies. So yeah, I understand like for something fresh, it's hard to know where to start. But as you see different problems, you develop strategies. All right. Any other questions with this one? Okay. All right, let's look at number 4. Okay. So we're going to prove that A united with B minus C is A united B minus C minus A. Okay, so I think we can do this with the laws. Okay, so let me say that this is the more complicated side. And we're going to start with this one. Okay, and I want to transform it into the left-hand side. All right, now subtraction is not part of the table above, but we need to remember what set subtraction means. So set subtraction, if I have two sets, like C minus A, then I think when we first looked at set, we saw a definition of set subtraction. That means that C minus A means that an element is in C, but not in A. So the way we can write that is that it's C and not in A. Right? So C minus A is equivalent to C intersect the complement of A. Okay? So this will help us change things to intersections, and then we can use the laws in the table. All right, so let's first change this subtraction. So this is going to be AUB minus C intersect AC. Okay, and then let's change this subtraction. So basically it's like you have this set minus this set. So by the same rule, this is going to change into the first set intersected with not, or the complement of the second set. Okay, so that's kind of from the definition of subtraction. It says that it's the first set intersected and not the second set. All right, so we change things to unions and intersections. So then we can apply some of the rules above. Okay, so I see this complement right here. I can do De Morgan's law. So I have A union B intersect with complement of C, and the union A complement turns into A, so negating a negation. All right, so here I am so far. All right, and now this looks like the distributive law again, because I have like A appears it's common to both of them, and you have like union and intersection. So with the distributive law right here, I can pull out the A. So this is going to be A united with B intersect with a complement of C. Okay, so I'm doing the distributive law backwards. Okay, so where do I'm trying to get to here. Okay, so I'm almost there because I have the A union part, but this needs to be changed back to a subtraction. Okay, so, right, so B and not C basically. This is the definition of the subtraction. So we change that, format the intersection back to a subtraction, and I get to what I needed. Okay, so I transform like the more complicated side into the simpler side, and that proved the equality.
Professor, I have a
Yeah.
question. So to me, like the subtraction operator, I don't know, it seems kind of weird. So is it possible to solve these problems by, as opposed to just attacking one side and trying to make it seem like the other, as like changing both sides, like
No.
modifying one side and modifying the other?
Yeah, so these proofs are just like trig proofs that you learned a while ago. Like if you're trying to prove equality, you're trying to prove like an identity, you don't work in parallel. You basically have to pick one side
I see.
and apply the rules to change it into the other. You can work on both sides at the same time.
Now, theoretically, could you work on both sides at the same time, and then once you reach a you know, the same, you have the same thing on both sides, then do the inverse of the other?
Absolutely. So yeah, in practice, that's a really good strategy. Yeah, you can simplify both sides and then work backwards to kind of follow the steps through. Yeah.
Okay,
I
thank
like
you.
that idea. All right, any other questions with this? All right, so this is the end of section 4.2. This was a fairly short one, just kind of a continuation of proving things with sets from section 4.1. So we're going to, let me pull up quiz 7. Where is quiz 7? Do I have quiz 7? Probably. Yeah, there it is. All right, so quiz 7, I've actually covered all the ones before the spring break. So yeah, quiz 7 was in sections 3.8, 3.9, and 4.1. So I'll try to post quiz 8 soon, maybe tonight or tomorrow, so you guys can start looking at it. So that will cover the next 3 sections, like 4.2 and the first couple of sections in the number theory chapter. All right. But we are now going to start looking at number theory. All right, so basically we're going to use all those lovely logic laws and methods of proofs that we've learned so far to learn about other topics. Okay, so the rest of the semester, so this half of the semester, the first half was basically the terminology and sort of the logic laws and set theory and all that stuff, and learning how to do a few proofs. And now we're going to apply those. So we're not leaving them behind. They're gonna kind of keep popping up as we do things. But we're going to look at first number theory, and then we're gonna look at relationships and functions. Then we'll look at sequences and recursion, and kind of related to that at sort of algorithms. And we might have a little bit of time for graph theory. That's a bonus if we get there. All right. So like all these topics, we'll see proofs and we'll see sets and we'll see a bunch of other things that we've developed over this the first half of the semester. So number theory is useful in like computer science for lots of reasons. I mean, computer science, when you program stuff, you're dealing with numbers, obviously. But in particular, kind of what's really relevant to today's age is all the password and encryption stuff, right? You have like, try not to have too many passwords, but every time you're going, you have to log into something, right? You log into your Canvas, you log into your Gmail, you log into this, that, and the other. And the passwords are encrypted. So basically, they're secret things so people don't get to your information, which can be personal and critical. You don't want people to know your medical history, your financial, your grades, all that stuff. So it has to be very strong encryption. So in order to do a good encryption on sensitive information, computers need to deal with really large numbers and doing arithmetic with large numbers, and in particular with large prime numbers. Okay, so a lot of the stuff that we're learning, especially in the couple of sections, is sort of setting up the terminology and the operations, the arithmetic that will lead us into talking about how the computers do operations on large numbers. So you'll notice that computers, I'm talking to them like they're people, but but anyway, computers don't like to do things the same way as humans do. The way we approach certain algorithms like addition, multiplication, division, especially division, it's the way we learn it is efficient for the human brain, but that might not be so efficient when the computer is working on them, because computers work in sort of repetition and loops rather than sort of critical thinking, although that's probably going to develop pretty quick. So you might kind of look at this as like, why would I want to do things that way? But kind of keep in mind that it's not you doing it. It's sort of how do you tell the computer to do something, an algorithm, in the most efficient way, so it doesn't take the computer a long time to do. Okay, so that's kind of a preamble to it. So, so a lot of, yeah, go ahead.
And that ties into linear algebra a lot as well, right?
Oh yes, absolutely. Yes,
Okay.
this definitely ties into linear algebra. Okay, so we're going to look at some arithmetic. So particularly divisibility of numbers and modular arithmetic. That's kind of our starting point. So we define division, okay? So a and b are integers. We say a is not 0 because we want to divide by a. We say that a divides b if there is an integer c. So b equals a times c. Okay, so basically b divided by a is an integer. So a divides b is equivalent to saying that b is divided by a, right? So when a divides b, a is a factor or divisor of b, and b is a multiple of a. So this is all sort of stuff that you're familiar with. But this notation might be new, right? So this notation with a vertical bar, this says a divides b, which means that b can be written as a times an integer.
And why do we use this notation instead of fractions?
Because it's, I think
it
it's
ends in true or false, right?
It's
These
a
are
what?
equal to true or false. These that bar. So
Yeah.
that 4 with that bar, then 20 should be like equal to true or false, right? Not a
Is
number.
it? I guess I'm not. You. Some of you might be more familiar to like where this notation comes from. My take on it is that this was developed by computer scientists, and sort of in parallel to a lot of the math that kind of happened. So yeah, not sure why this is used instead of fractions, but it's sort of it's just a notation for saying that a divides b. Okay. So yeah, a lot of this stuff was sort of developed in parallel by different disciplines, and it kind of its notation that sort of lasts, but it's equivalent to other notation from another discipline. So I think this was more developed in the computer science field, when sort of number theory.
Is this the same as just saying the remainder is 0?
Yes. Okay, so if a divides b, then the remainder is 0. So b is a multiple of a. Yeah, it does say that also. Okay, so let's look at example 1. So let's see, determine whether these numbers divide by the others. So does 4 divide 20? Right. So 4 divides 20 because I can write 20 as 4 times an integer. Okay. Does 20 divide 4? 20 does not divide 4.
No.
Because that would mean I would have to write 4 as 20 times an integer. And that's not true because 4 is 20 times 1 over 5, and this is not an integer. All right, so that's a no. All right, does 0 divide 5? Can I write 5 as an integer, as 0
No.
times an integer?
No, because any number will be any integer multiplied by 0 will be 0.
Exactly. And that's also kind of breaks this, right? That a can equal to 0 because that means you're dividing by 0. All right, cool. All right, let's go to the next one. All right, so let's look at this theorem. All right, so we're kind of again establishing some rules for division. Okay, so this theorem says if a and b and c are integer and a is not 0, then these 3 things. Okay, so let's we're gonna prove them. All right. So if a divides b and a divides c, then A divides B plus C. Okay, so a direct proof would probably be a good place to start here. Notice that this is what we're doing not too long ago. These are my premises, and we're trying to prove this conclusion right here. So starting with our premises being true, we want to prove that this conclusion is true. Okay, so let's look at what our premises say. So A divides B by the definition above. That means B can be written as A times an integer. And A divides C means that C can be written as A times an integer. We don't want to use the same integer because that will basically make it a special case where B equals C. And we want to be able to say that this is true in the most general case possible. Okay, so K and L are both integers. Okay, so basically we write the premises using that definition of division. All right, now to prove the conclusion, I'm trying to see if A divides B plus C. So let's use these premises together and we're going to add them because that way I can get the B plus C. So if I add the two equations, then B plus C equals AK plus AL. B plus C is going to equal A times A plus L. All right, so does A divide B plus C? We're going to say, yeah, because this right here is an integer. So because I can write this number as A times an integer, then that means that A is going to divide B plus C. Okay, and that's it. That's the end of the proof. Okay, any questions with that one? All right, let's look at number 2. Okay. Actually, number 2, we can sort of continue. Let me okay, let's see. My chat is hidden. Let me make sure that there we go. Okay. All right, so let's look at number 2. So number 2, if A divides B, then A divides BC for all integers C. Okay, so let's look at this. So if A divides B, then just as before, I can write A, I can write B as an integer times A. All right, now I want to see if A divides BC. Okay, so I need to transform this so I have BC in here. So I'm going to multiply both sides by C. So I'm going to multiply both sides by C like this. So I get BC equals A times KC. All right, now if A divides BC, then BC can be written as A times an integer. So because K is an integer and C is an integer, then that is fulfilled. So A is going to divide BC. Okay, so that proves that one. Okay. Any questions so far? All right, how about I let you guys try 3. So 3 says if A divides B and B divides C, then A divides C. Notice it's like a chain rule thing, right? Okay, so I'm going to give you guys a couple of minutes to try it out. All right, so let's look at this. Okay. I want to find some space. I gotta clear this. Okay. So number 3. So if A divides B and B divides C, then A divides C. Okay, so again, these are my premises, and that's the conclusion. So we can take each premise and write it. So if A divides B, then this means B equals A times some integer. Okay. If B divides C, then C equals B times another kind of integer. K and L are integers. All right, and what's the next step? What should I do with these? Any ideas?
Combine them.
Combine them, yeah. So combine them by, right, I see a B here. I can plug in the B there. So I have C equals AKL. And let's separate them. C equals A times KL. Okay. So this does it, right? This proves it because this is an integer. So because C is A times an integer, then that means A divides into C. A divides C. Yeah, A divides into C, same thing. Okay, so here's my conclusion. All right, so what this theorem does, if you notice, it kind of established some rules of operation, right, with this division thing, right? So I'm kind of going from the definition of divisibility, like A divides a number, by saying, here's a rule for adding, here's a rule for multiplying, here's a chain rule. So these are sort of useful along the way as we're working through these problems. Okay. Any questions with that theorem? Okay. All right, let's go to the next part. Let's look at this theorem. Okay, so this theorem says A, B, C are integer, A is not equal to 0, such that A divides B and A divides C, then A divides MB plus NC whenever N and M are integers. So this is like a little bit of a combination of the first two parts of the last theorem, because it's sort of this is like a linear combination of B and C. So we're multiplying and adding at the same time, right? So let's see. We start with our premises. So A divides B and A divides C. So we're going to do the same as above. So B is going to be A times an integer. C is going to be A times a different integer. So both of these are integers. Okay. All right. So what I need to get here. Okay, so if I'm looking at my conclusion, I need this expression somehow. Right. So in order to take what I have in the premises and come up with that expression, I should multiply this by M and multiplies this by N and then add them up. Okay, so let's multiply first. So this gives me MB is AKM and C equals ALN. Now we're going to add these together. So basically my goal is to get this expression somehow, right? So MB plus NC is going to be A times KM plus LN. All right, cool. And this is basically done because what this says is that I have this number here equals A times something that's an integer. okay, because K and M and L and N are both all integers. This sort of sum product thing is going to be an integer itself. So because this number is A times an integer, then A is going to divide MB plus NC. Okay? So this says it's A divides B and A divides C. A is going to divide any linear combination of those numbers B and C. Okay? So it's sort of a more generalized theorem than the parts 1 and 2 combined above. All right, any questions with this one?
So normally we don't put parentheses on the right side, right?
It's I don't know. Normally, it's a good word. Yes. So yeah. Often parentheses are skipped here. So if you see this division, it's kind of implied that it's A is dividing this whole thing, not just the first part. Okay. I often put parentheses just to not confuse myself or people. But yeah, if you don't see parentheses, then it's like assume that it means that A divides into this whole expression. Okay. Any other questions? All right. Okay, so let's look at the next thing. The division algorithm. All right, so what basically this says is what we know about division already, but it introduces a little bit of kind of notation language. All right, so what this says right here is that if I have a number A, an integer A, and I divide it by an integer D, then the division might not be exact. You might get a remainder, okay? So if I divide an integer A by an integer D, then I'm going to get Q, which is the whole number part, and the remainder R, which is the remainder part, okay? So Q is called the quotient and R is called the remainder. And these are sort of language that we're going to use often from now on. So A div D means what whole number, what's the quotient that I get from dividing A by D. Right? And A mod D is what's the remainder that I get from that division. So this mod is, we'll see the mod more often than the div. This modular arithmetic is really important in computer science. And we've seen modular arithmetic a lot in real life without realizing. Like when you read a clock, it's like base 12 and you do modular arithmetic by going, okay, how many hours are between 8 a.m. and 2 p.m., right? Like you're doing modular arithmetic, okay? So, we're going to use this modular stuff quite a bit over the next few sections. So a kind of important part here to remember is that the remainder is a positive number, actually a non-negative number, because you could have zero remainder, that is less than D, it's less than the divisor, okay? Just sometimes people make the mistake of making the remainder negative, and that's not allowed. The remainder has to be non-negative. All right, so let's look at example 4. Okay, so we're going to example 4a. Basically, we're going to take 101 and divide it by 11. Okay, so we take 101 divided by 11, and 101 div 11 gives me what the division, what the whole part of the division is, right? So if I divide 101 by 11, I get 9, right? Okay, and the mod gives you the remainder. Okay, so I do the division, I get a 9, but then the remainder is going to be 101 minus 99, which is 2. So the 9 is the whole number and the 2 is the remainder. Okay. All right, and sort of kind of just following that equation right here, that basically says that I can write 101 as 11 times 9 plus 2. So I can write any integer by this formula that says it's the divisor times the answer times the question plus the remainder. So 99 plus 2 gives me 101. All right. So part B, I'm going to divide negative 11 divided by 3. Okay. So if I do negative 11, I want these two numbers. Okay, so what's negative 11 divided by 3? You guys help me out.
11 divided by 3.
Yeah,
It is 3, remainder 2.
is it negative 3?
No. Oh, negative 11? Oh,
Negative 11 divided by
genius.
3.
Right,
It's,
but what did that
it's
give us?
negative
A
4.
negative remainder?
Yeah, so negative 3, it's not incorrect, but this will give me a remainder of negative 2, right? Because if I say
You
negative
say
11,
that you can't have a
I
negative
can't have a
remainder.
negative remainder, right? So if I say it's negative 3, then it works out, but R can't be negative. Okay, so this is not the best choice there. Okay, so what should I say?
Negative 4.
Negative 4. All right, so if I say negative 4, right, then I have negative 12, which gives me a remainder of positive 1. Okay, so I can write negative 11 as 3 times negative 4, which is negative 12, with a remainder of positive 1. Okay?
Well, actually, R have to be less than D, right?
It has to be less than D, right? So yeah, it has to be a positive number that's less than what you're dividing by. So you don't want to have a remainder that's bigger than 3, right? Because you're not dividing enough, right? So you basically want to reduce it as much as possible, but still have a positive remainder. Okay? All right, questions with that one? All right, cool. All right, let's see next. Okay, so now we're going to talk about congruencies. Okay, so basically congruencies in modulo. Okay, so we have this concept of A is congruent to B modulo M. Right, so we have two integers, A and B, and we have M, which is a number that we're dividing by, right? And we say that these two numbers, A and B, are congruent to each other in that modulo M if M divides A minus B, right? And that's the notation for a congruency. So congruency in math, if you kind of think of geometry, like this is congruent with that, means some sort of equality, right? Like these two things are the same size or they're equal to each other. But congruent in modulo doesn't mean that the numbers A and B are equal to each other. It means that their remainders, when you divide by M, are going to equal to each other. Okay, so two numbers being congruent in modulo. So this theorem right here explains that basically. If A and B are congruent in modulo M, it is if A mod M is the same as B mod M. So when I divide A by M, I get the same remainder than when I divide B by M. Okay? So, cool. Okay, so you can think of this as trig again. I don't know why I keep mentioning trig, right? So let's think of the unit circle, right? Okay, in the unit circle, the modulo is like that makes sense, is like 2 pi or 360 degrees, okay? So if I give you two angles, let's say I give you 45 degrees and I give you 405 degrees. So if I have an angle of 45 degrees and I have an angle of 405 degrees. 4, 5, 6, 60. Yeah, okay. So these values are definitely not the same value, right? 45 is not equal to 405. But they're congruent in modulo m. They're congruent on the unit circle because it represents the same angle. As I'm winding through the unit circle, it represents this the same place on the unit circle. Okay, so that's kind of an example of kind of congruency in modulo that you've already come across. So, all right, does that make sense? Any questions so far? All right, okay, so let's look at doing stuff here, okay? So we're going to determine whether 17 is congruent to 5 modulo 6 and whether 24 and 14 are congruent modulo 6. Okay, so there's two problems here. So let's look at this one first. Okay, so there's two ways to show this. It's congruency. You can either show it with this or we can show it with this. Okay, so the first way, right, if I want to see if 17 is congruent to 5 modulo 6, I want to figure out whether 6 divides into the difference between those two numbers, okay? So that's a question mark. So does 6 divide 17 minus 5? And that's a yes, because 6 divides 12. Okay, so you say that's yes, 17 is congruent to 5 modulo 6. The other way to show it is to look at separately at the remainders. So if I do 17 mod 6, what is that? So if I divide 17 by 6, what's the remainder? Is it 5?
I believe so.
Because 6 goes in 17 twice with a remainder of
And then also with 5, it would also be the same remainder.
yeah, so 5 mod 6, 5 divided by 6 is 0 with a remainder of 5. So because they have the same remainder, they are congruent. 17 and 5 are congruent in modulo 6. Okay? All right, let's look at 24 and 14. Okay? So our 24 and 14 congruent modulo 6. So first way to do it is to take the difference. All right, and check. Now 6 doesn't divide into 10, so no, they're not congruent. Okay, so another way to look at it is by finding the remainder. So if I do 24 mod 6, 24 divides by 6 goes 4 times with the remainder of 0, and 14 is not a remainder of 0, right? It's a remainder of 2. So these are not the same. So 24 and 14 are not congruent mod 6. Again, the discongruency basically means you get the same remainder when you divide those numbers by m. Okay. All right, any questions with that?
So the parentheses, again, outside the module M, like does it make any difference between this and just being mod M?
So like this notation is, especially like there's some of it is bold and some of it is not. So this is, so this notation is like for the congruency. So this says that A is B congruent, A is congruent to B mod M. And when you have like without the parentheses, when you're saying A mod M like this, then you're going, oh, find the remainder of this division. Okay. So this is like where I'm not finding the remainder of B divided by M. It's a statement about the congruency between A and B in mod M. Okay, so it's kind of like this.
Okay.
It's really, maybe the bar is not the best idea. So, I'm making this I'm making this statement right here. I'm saying A is congruent to B, and in parentheses, in mod M. Okay, so it's like this mod M is not an operation on B. Yeah, I'm specifying that A is congruent to B under that condition.
So M is like the previous called B, right?
The what?
Like M here is like previously called B. Like we used to have A bar B, right? And now we have A, B, and then bar M.
Because let's see,
Like
A bar B is like A divides B. Are they related? Yeah, it's bar M, exactly, because it's like you're dividing both A and B by M. So yeah, you're like, if you look here, it's like, yes, that M is what divides into both numbers. So yeah, the M is the thing that you're dividing by, basically. All right, okay. Let's look at the next problems. Let's see. Okay, cool. Okay, so let's establish a few more relationships between they have to do with congruency now, but also division. All right, so this theorem says if M is a positive integer, then integers A and B are congruent modulo M if and only if there's an integer K such that A equals B plus Km. All right. So the premise is that A is congruent to B mod M. All right, and I want to prove that A equals B plus Km. I actually want to prove it both ways, right? If and only if, right? So I need to show that it works both ways. Okay, so the first case is that I'm going to assume this is the premise, and I want to prove this. All right, and then the second case is going backwards. Okay, so if A is congruent to B mod M, by the definition of it, that means that M divides into B minus A. Okay, now if M divides into B minus A, that means that this number B minus A can be written as M times an integer. So that's by the definition of that division. Okay, and oh, did I get I think I got them reversed. Which is okay. I could have picked the K to be a negative number, but let's just do it in order. So M divides into A minus B. So that means A minus B is M times an integer. Okay, now add B to both sides, and we get that A equals B plus Km. All right, so that shows the theorem working this way, in that direction. Okay, now let's look at the reverse, which is basically the same steps but backwards in this case. So we're going to assume this is true, and we're going to try to prove that the congruency is true. Okay, so starting with this as my premise, I'm going to subtract B from both sides. I see that this number A minus B can be written as an integer times A times M, which means M divides into A minus B. And because M divides into A minus B by the definition of congruency, that means that A is congruent to B mod M. Okay? Right, so that's how we established this theorem right here. All right, so these sort of, they kind of lead into each other. They might seem like a little bit disjointed, like it's like, oh yeah, another fact. But it's sort of, again, this section and the next one, it's kind of building a structure for some of the stuff that we'll see a little bit later. So we'll kind of need all this structure in order to do some of the more complex things. All right, questions on this one? All right. Let's see. Oops. Mouse. There we go. Okay, another theorem. So let m be a positive integer. If a is congruent with b mod m and c is congruent with d mod m, then a plus b is congruent to b plus d mod m, and ac is congruent to bd mod m. Okay, so again, sort of this kind of establishes some addition and multiplication properties of congruency, right? So let's prove it. So we start with knowing that a is congruent to b mod m, and c is congruent to d mod m. Okay, so from here, using the definitions, that says that m divides into a minus b, and m divides into c minus d. All right, this means that a minus b can be written as m times an integer. And this means that c minus d can be written as m times another integer. So k, l are both integers. All right, so this will help us with these things. Okay, so basically I see that I want to find like some addition or some multiplication properties. All right, so from here, actually, I could have probably skipped a step here using the last theorem, because by what the last theorem says, that means that A can be written as B plus MK, and C can be written as D plus ML. All right. Okay, so if I want to prove this, I'm going to add these equations together. I'm going to say A plus C is B plus D, and M K plus L. Okay, so because I have this number can be written as this plus M times an integer, then that means these numbers are congruent in that mod. So that's using the last theorem. That means A plus C is congruent to B plus D mod M. All right. And if I multiply these together, if I do A times C is B plus MK, D plus ML. This is going to give me BD and BML, DMK, M squared KL. So AC is going to be BD plus M times a bunch of stuff, okay? So what's important is not what the bunch of stuff is, whether the bunch of stuff is an integer. So this thing in parentheses is an integer. So because this number can be written as this number plus m times an integer, that means these are congruent. Okay, so AC is congruent with BD in mod m. Like that. Okay, so this establishes kind of the addition and multiplication properties with congruencies. All right. So let's use these properties here in example 8 to kind of show how simplification can occur. Okay, so let me get rid of this. Okay, so this example uses these properties. So let's look at them. So if 7 is 2 mod 5 and 11 is 1 mod 5, then show that 18 is 3 mod 5 and 77 is 2 mod 5. So we can see that the 18 we can obtain by using the addition property above, right? Because if I add these together, I have 7 plus 11 is going to equal to 2 plus 1 mod 5. So this just uses this property here, right? So when you simplify, I get that 18 is congruent to 3 mod 5. Okay, so that shows that that's true, right? And to get this one, we can use the multiplication property. So if I multiply 7 times 11, that's going to be congruent to 2 times 1 mod 5. So we get 77 is congruent to 2 mod 5. So that shows this one, okay? So this just allows for manipulation. So you can manipulate things, operations, and congruencies to simplify or to expand, and basically just to do arithmetic with them. Okay, so that's kind of what we're doing. We're establishing some rules so we can manipulate and do arithmetic with these mods. All right, any questions on that? All right, cool. Let me see if I can finish up because I don't have that much time left. Okay, let me do 10 first, and then I'll come back to 9. We'll see 9 again. So arithmetic modulo m, so you'll see these symbols. Right, so plus in modulo m and times in modulo m. So basically, if you add two numbers in modulo, means that you are adding them and then finding the remainder when divided by m, and same with multiplication. If you're multiplying in modulo, you're multiplying the numbers and finding the remainder. So if I want to do 7 plus 9 in modulo 11, then I'm going to add the numbers and then find the remainder when I divide by 11. That's going to be 5. And if I do 7 times 9 in modulo 11, I multiply the numbers and I find the remainder. So that's going to be 5, 8. Okay, so 55, 63 minus 55 is 8. Okay, so that's kind of some arithmetic or operations in modulo. All right, cool. So let me go back to the previous one and talk about that one. Okay, so yeah, we'll see this again as we work through more complex problems. I'm not going to prove this theorem, but basically, again, it allows for simplification or expansion of things in modulo. So the first one right here says if I have a sum of a plus p mod m, I can expand it like this: a mod m, b mod m, mod m. If I have a product, then I can expand it like this. So this kind of allows you to break up bigger numbers into smaller ones. So I guess maybe not how humans think, but definitely computers kind of find the simplification more efficient. Okay, so for part A, for example, if I have 177 mod 31 plus 270 mod 31 mod 31. So this is this format right here. So basically you can see that it's the same mod of the same number, mod 31, mod 31, mod 31. Then I can simplify this to write 177 plus 270 mod 31. I can add these numbers, mod 31. And then we do it, okay? So we divide 447 by 31. we get 14, but we need to find the remainder. So 447 minus 14 times 31. I find a remainder of 13. Okay, so we could have done all separately. We could have found this remainder separately, add them up, and then found the remainder. That still would have given us 13. Or you can sort of contract it and do the operation that way. Okay, so in this next section, we'll see this again, how we can use this to kind of expand and contract things as needed. All right, so that's it. This is the end of section 4R41. Okay, quiz 7 is due on Thursday, but quiz 7 is 3839 and 4.1, the set theory. So we've already covered that material. Stick around for office hours if you guys have questions on this or anything on the quiz. I can address those questions. All right, great to see you guys. I'll see you Thursday.
For the writing technology assignments, are we allowed to, like, if I pick the logic, if I pick one of the logic options, could I do the other logic option for the next one, or do I have to pick a different topic?
No, just you can, for those, always just pick whatever you like, as long as you don't do the same twice.
Okay.
So yeah, whatever, it's like, it doesn't have to sort of fit with what we're doing at the moment, although it's probably better that way if we pick a topic that we're sort of studying at the time. But yeah, if you want to pick two of the same topics from two of the same problems from the same topic, you can. No problem with that.
And then I was trying to find the feedback on the test on where I made a mistake, and I couldn't find it. So I don't know if you put it.
All right, let me look at yours and see what it looks like. I'm not gonna share the screen. I'm just gonna check and see if I can direct you. Maybe you can share the screen with me, but oh no, I don't want that either. Unless we're meeting one-on-one, I don't want to show grades. All right, so let's look at this. Let's test.
I really like the overnight format, by the way, because I woke up in the morning and I looked at it again and I realized I made a bunch of mathematical errors. Like,
yeah, it's nice to have thinking time, definitely.
Yeah, so I definitely appreciate that, because I made a bunch of small errors and then I looked at it again in the morning. I'm like, so definitely like that. All
right. So I think you should be able to see it. So let me see if I can direct you a bit. Okay. I think I might need to go to another class. Let's see. Oops, that's not it. All right, let me share my screen. Okay, so if you go to grades, like click on grades, all right, and you sort of scroll down the list, and this is not our class, so it's different assignments. Don't freak out if you don't see quiz this and the other, but I know I uploaded something on here. All right. Okay, so click on where it says test 2. So you took your test 2 and you should be able to click on it from the grade book. You will see this screen right here. Okay, so these are like the files that you submitted. And if you click on view feedback, then you see the submissions with my markings on it. So you should see like red check marks or comments or cross marks. Okay, so this is where, and I think you can extend this somewhat. All right, so it's the view feedback button, view feedback from the gradebook.
I see the view feedback, but
Mhm.
I checked through all of the documents I couldn't find where I lost some points. I know I submitted like a whole bunch of documents though. So
Did you, are you able to see any of my check marks and stuff?
I do see your check marks. Maybe it's a little bit harder to see because I use different colors too on mine, and you use the red.
So, okay. You're trying to figure out where you lost points?
Yeah, I'm trying to figure out where my mistake was so I don't make it again during the final.
Did you lose points?
Yeah, I did.
I don't think you did.
Really?
I think you're trying to find points off and you don't have any.
Wasn't it out of 110?
No, the extra credit is 5 points.
Oh, okay.
Right.
Okay.
So there is an extra credit problem, but the extra credit problem is worth 5 points, not 10.
Okay, I thought it was 10. That's
Okay. Now I see. I'm trying to figure out. Yes. Yeah, you
And I
did
actually
lose
feel
it.
better about this test compared to the first one. It took a lot longer, but definitely much happier about it.
You like the format better? Okay.
Yeah, because I feel like at least for work, you know, a lot of the times we can't solve the problems right away, but we do a lot of research. So I kind of took the same approach to the test that for anything I really had trouble with, and I just kind of reviewed a lot of material, and then some of them I kind of solved like early morning on the Friday morning.
Yeah.
Reviewing it.
Cool. Congratulations. That was good.
Thanks. Yeah, you feel better. A lot better than the first test.
Awesome.
Professor?
I have a question, a confused on quiz 7 for question 4B and 4D.
Okay, so quiz 7, let me pull it up. It's quiz 7, 4.
For B and D. For the question for B and D.
So 4B. Okay, so P refers to this statement right here. X plus 2y equals xy. Right, so we want to determine the truth value of this. Okay, so what this says is that there exists an x such that for all y, this statement is true. Okay, so basically this says that there's a particular value of x, all right, for which this equality is true no matter what you plug in for y.
Okay.
Do you think that's true?
No.
No, yeah, this is false. Right? So yeah, because you're basically saying it's like it doesn't matter what I plug in for y, this will always be true, and that's not correct because it's only going to be true for a specific value of y. Okay. All right. Which other was?
And the other one is D. So is it the same for with B?
Sorry, I just did B.
Yeah. And how about D?
Are we also
He said
talking
D as in duck.
D?
D as in duck.
Yeah.
D. Okay, so D. Okay, so D, we're switching the order, right? So this is for every y, there exists an x, so P of xy is true. Okay, so this means that for every y value, there's going to be an x value that makes that true. So for every y value, this will have a true solution. Okay, so another way that it's asking, it's like, can I solve this for x or an arbitrary value of y? Can I? So if I do it, like if let's say I subtract x from both sides and I factor it, I get x equals 2y over y minus 1. All right. So does this have a solution for every y value?
No.
No, because it doesn't work
Y equals 0.
when y equals 1, right? If that wasn't divided, then it wouldn't been true. But because it fails, this doesn't have a solution, y equals 1, then this is also going to be false.
Can I say when I change the x and y, the order doesn't matter. Like the result will be same. Like D equals to B. Can I say that?
D equals to
B. Because we only change the order of x and y.
No, if you change the order of the statements, then it has a different meaning.
Okay.
So B and D are different because in B the existential comes first. But you're saying if I'm changing the x and y.
No, I'm saying changing the prepositions.
Yeah. So if it's mixed prepositions, existential and universal, if you change the order, it has different meanings. So yeah, the meaning of B is different than the meaning of D. So the meaning of D says that am I able to find a solution for X for every value of Y? Okay. But the meaning of B is that for one particular value of X, this equation would work for every value of Y, which means, like, let's say I pick 2 for X. Then that statement means that for this particular value of X for 2, this equation is true no matter what Y is. Okay. But it's like, it's not really X is 2. It's like, can I find the value of X where that equation is true for any value of Y? Okay. And that's not true. I don't think you can find infinite solutions to this equation if y is arbitrary.
So what is the relationship between the axis and on symbols?
What's the relationship between this and that?
Yeah.
Well, they say different things.
So I mean, if I have is x on y, it means like there is an s for y for all y, right?
So if there exists an x for all y?
Yes. It means there is an s for y.
Yeah, so this means that there exists one x so that this statement is true for all y values.
Oh.
Okay, but if I write this, it means that for every y value, there exists an x, so this is true, okay? So this one, like the x values would match with the y value. So it's like for every y value that I can think of, I can find an x value for each of those y values where this is true, okay? All right, so this is like basically saying, yeah, I can solve this equation. I have this equation x and y, and if I have a y value, then I can figure out an x value that solves that equation, okay? And this is almost true. I mean, if this is not true because of this division by 0, but for all the other y values that are not equal to 1, you can find the value of x where that equation is true, right? But the top statement here says there's a fixed value of x. There's one value of x where this statement is true no matter what I plug in for y. Okay. So yeah, these are definitely different from each other. They have different meanings.
So I understand that they have different meanings, but I guess my reasoning for B and D were pretty similar in that, like for D, it doesn't work if y equals 1.
Mm-hmm.
But can we say that that same reasoning is true for B? Because it could be true for all x values, but
it's not, you're not looking at all x values. It's not the reverse. You're not saying that for every x value you can find a y. You're saying that for this one particular value of x, the equation is true no matter what y value you pick. Right.
So if we say that it's false, do you want us to provide a counterexample?
It's not necessary. I think an explanation is better. I think that a counterexample for B would be really hard.
Okay.
So let me give another example. Let's say P of x is x plus y equals 5. Let's get something simpler, okay? So part B says there exists an x such that for every y, this statement is true. Okay, so what this is saying here is that I can find one value of x. So no matter what I plug in for y, this statement will always be true. Okay, so this is saying that there is one value of x only, that if I plug in x, y is 1, this is true. If I plug y is 2, this is true. If I plug y is 3, this is true, and so on. But this x is fixed. There exists one x for which this equation is true no matter what I plug in for y. Okay, so that's the meaning of this order. Does that make sense?
It does, thank you.
Okay, now
I was also, sorry.
Now what D says, all right, so let's look at the reverse. What D says is that for each y, for every y, there exists an x that makes this true. Okay, so that means that for y is 1, I can find an x which makes that true. And yeah, I can find x is 4. For y is 2, I can find an x that makes that true. Yes, I can find x is 3. All right, so there's like, indeed, there's nothing that's fixed. All right, so like this one in B, like that, each, like there exists an x, that value is fixed as you vary the y. But in D, each y, there exists an x, like the x is paired up with the y, so x changes at the same time that y does. So you can actually, you know, that would be true because you can find value of x that make that equation true.
Okay, thank you. That's actually
Thank you.
Okay.
I understand it right now.
All right. Yeah, these you have to kind of twist your brain to see why they're different. Yeah.
I actually have a question on F as well. I wondered if you could go over F.
All right. So F. Okay. So you want to distribute the negation. All right, so you want to simplify it to distribute the negation. So when the negation needs to pass through all the quantifiers to go to the proposition. So if you pass this through every, is going to turn into an existential. It passes through an existential, it turns it to every, and then it's going to negate whatever was there, right? So this turns into there exists an x such that for every y, pxy. Right, so you transform it into this, and then this is b. So this is the same as b.
So you don't change the x's and y's, you just change the operators?
Yes, yeah, so the negation passes through the operator and it changes, right, the universal to an existential, the existential to a universal. It's kind of like the Morgan's law. And then that negative migrates to the whatever the proposition is.
Okay, thank you for clarifying that.
Okay.
So when you change the negation of all x, doesn't it make it all x, not just one x?
The negation of all x,
Yeah.
turns into there exists an x such that p is not true. So the negation changes all to e, and it goes in front of the proposition.
But not negation of all x, does it equals to exist x?
Yeah, the negation of all x is equal to there exists x of the negative of the proposition.
Oh, okay.
So yeah, that negation doesn't vanish. It goes in front of your proposition.
I guess my question is, not all it is exist, right? I mean, not all is the negation of all.
Oh, not. So how do you say it? So let's see. So yeah, the negation of, so there's like for all x, p of x is true. To negate it, it's like, it's not true that for all x, p of x is true.
Okay.
So you wouldn't say that not, yeah, I guess you could say, basically this says that p of x is not true, or not all of x makes p of x true. Yeah, so basically say not all of x makes p of x true, which means that there exists an x for which p of x is not true. So yeah, you can say it that way.
Could you go over 15E, please?
15.
Letter E.
Which one?
E.
E. So A and B and C are sets. If A is a subset of B, then the Cartesian product is the subset of the Cartesian product.
Is it possible that that's one of the laws, like a distributive property, maybe? Could you say that?
It's not a lot that's written in any table, but it's probably, once you prove it, it's a law, right?
Yeah, I see. So problems like these, like it makes sense to me, but how do you like write it into
Yeah,
something
how do you write it?
that's
And
not as an answer?
I think you want to write it like, I think with the membership stuff, it probably makes sense. Okay, so if say if A is a subset of B, then that means if I have X is an element of A, then that implies that X is also an element of B. All right. Now let's look at the Cartesian products. The Cartesian products of A and C is all the pairs X, Y, such that X is in A and Y is in C. Okay, so that's kind of the definition of the Cartesian product. Okay, so it's this set right here. So it's the set of all ordered pairs, right? So now, because X is in A, X also has to be in B. Okay. So if I look at this Cartesian product here, like if X is in B and Y is in C, this defines the Cartesian product of this. All right, so because if X is in A, it implies that also X has to be in B, and basically the Y's just pair up and have to go along with it, then this set here has to be a subset of that. Okay, because like this set of coordinate points are contained in this set of coordinate points because all the X value of the coordinate points are contained in B. Right, so you say A, X is a subset of B, X. Right? So it's kind of that, yeah, I think that's a sufficient explanation.
Okay, thank you.
Mm-hmm.
Thank you, Professor.
Say that again.
Thank you.
You're welcome.
For 15D, as in dog,
Mm-hmm.
well, I guess for 15 in general, do you want us to do this by membership, or can we do Venn diagrams? Does it matter which? Do you have a
It doesn't matter. So I
Okay.
kind of left it open that you guys can pick
Okay.
whatever method that you want.
Cool.
I
So
find the proofs with subsets
Mhm.
are probably easier if you do with membership.
Okay. Okay. So then for D, at first I had thought maybe a Venn diagram, but it's an if and only if. So I didn't know if you could even use a Venn diagram for.
I think they're hard to draw with subsets. I
Okay.
think it kind of gets a bit confusing.
Okay.
Yeah, so I would do like if we try with memberships, right? So if A is a subset of B, that means that if X is in A, then X is also going to be in B. All right. Okay. So what am I trying to show? So if and only if the complement of B is in the complement of A. Okay, so let's set this up as
positive here, but I don't know really how to do that.
okay. So we set it up as a conditional. Okay, so basically, if A is a subset of B, then that means that if X is in A, then X is in B. Does that make sense? Right, so that's kind of the definition of a subset. If X is a member of A, then X is a member of B. Okay, so think of these as propositions, P and Q. So what I know about propositions is that I can do the contrapositive. So the contrapositive of this is not Q, then not P. So the contrapositive, the negation of Q is that X is not in B, and that's going to imply X is not in A. All right, so if X is not in B, then X is not in A, leads us to what this says. Right, so if X is not in B, right, then BC has to be a subset of AC. So kind of using a conditional here.
Okay.
Right. So
I didn't know if there were more steps, or if I could just say that if X is not in B, then it's the complement of B.
Yes, if X is not in B, then X is in the complement of B. Yeah,
Okay.
you can sort of write that extra step, but it's, yeah, you can jump from that to that.
Okay, thank you.
Professor,
Yeah.
can I get that question?
Oh, okay. All right. So let me, who is still around? Okay. So yeah, I need to put up a question for a couple of students. I'm going to kick some of you out. So office hours are over. So if you don't want us to, if you don't need to stick around, please don't stick around, because I want to do something with a couple of students. So I'll see you on Thursday. All right, so I'm gonna put a couple of questions up for you guys. All right, let me clear this up. I'll put one question up. All right, so let me write it. So I want you to prove the following. All right, so if I have P then R, Q then S, P or Q, then S or R. All right, so this is your question. So show all the steps and give me the justification with the appropriate laws for each step to show, to prove this. And when you're done, just take a picture and email it to me. Okay, so I'll stick around. Oh, I think about 10 minutes should be enough. Okay, but let me know if you need more time.
I can't see the question. It's frozen for me. Or...
Okay, let me. Can you see it now?
Yeah.
Okay, perfect.
I'm mute my mic, Professor. and just I should take a picture and just send it through your email. Yeah. You on mute.
Yeah, if you're done, take a picture and just email it. You can do it through Canvas.
Okay.
Yeah. You done?
Yeah.
Awesome, thanks.
And how long will this take to like be graded? And put it?
I'll do it now. I'll do it tonight.
Did you get it? I
Let
sent it.
me check. Looks like I got it.
Can you see it clearly, or should I use camera scan?
Let me see. Looks pretty clear. I'll just look. We got premise. We changed it. Use the chain rule. We changed it. Use the chain rule. Looks good. All right. Okay, it's graded. You're good. I'll give you your test grade.
Thank you.
Okay.
Appreciate it.
I'll change the grade right now.
Okay.
All right, bye. See you.
And one more question.
Yeah.
So for the writing assignments, every time I try to do it, it's like I always keep getting like a low grade, like a 16 or 17.
Yeah.
How would I take that to like a 20 out of 20?
Have you are you doing the writing or the computer programming ones?
Every one of them is the writing.
The writing. I would expand a little bit. So I think from what I remember, like you're giving me 2 or 3 examples, but they're very brief. So just doing a little bit more research and talking about each example in a little bit more detail, that will bring you to 20.
Okay.
Okay. All right.
Bye.
Bye.